Hi everyone, welcome to our review of waves. We're going to go through some different pages here. I would like you to read along with me. Many of the pages have animations. These animations will help you learn and understand more about the waves that we are going to study. Waves. Waves are traveling around you all the time as light and sound, but you cannot see those waves travel. To understand waves, we'll need a method of visualizing them as they move. Luckily, an easy way to do this is with a rope. We can move the rope and then observe how the kinetic energy moves across it. Suppose you have a rope in your hand and you raise your hand up and then back down to its original position. The energy from moving your hand travels across the rope as a single wave pulse, causing the rope to move as the animation shows below. In this scenario, the rope is the medium, or the substance made of matter that carries the wave. It's important to understand that a wave is a disturbance that transfers energy as it moves through a medium. The medium moves because of the wave, but it's not the wave. The wave is the transfer of your hand's kinetic energy across the rope. Waves like this one, which require a medium to carry them, are known as mechanical waves. Waves only move energy. There is another important quality of waves that we're missing, however. Let's see if we can understand it through observation. Look at the right at the picture of the duck. Watch these surface water waves. Carefully follow the movement of a wave as it travels across the screen. Then observe the movement of the duck. Consider how their relative motion compares. What does this tell us? For a hint, look at the little dots. Each one is a particle in the moving water. Answer: the wave is only moving energy. The particles in the duck move, but they don't go very far, and they always return to where they started. Mechanical waves in space. We observe mechanical waves daily, including sound. Sound is simply the energy something releases when it vibrates or moves back and forth. This energy, which we interpret as sound, travels through the air to our ears as waves. Outer space is generally considered to be a vacuum, a space with no matter. If we consider space to be a complete vacuum, how does this impact the propagation or traveling of sound waves? Remember, sound waves are mechanical waves. That means they can only travel through a medium. Now it's time for some wave anatomy and properties review. Mechanical wave classifications. Mechanical waves are classified into different types depending on the direction of the disturbance. Let's visualize this with the help of a slinky. Like the rope from earlier, we can use the slinky as a medium to see energy travel. Transverse mechanical waves. Suppose you're holding the slinky. You want to send energy down it, so you move your hand up and down and convert potential energy to kinetic energy. This energy travels down the slinky forward. When you move your hand this way, the disturbance caused by the wave is up and down. In other words, the particles of the medium move perpendicular to the direction the wave travels in. If this seems a bit confusing, look at the picture below. It has an animation of the direction of the particle motion, and it shows the direction the energy is traveling. The wave moves to the right, while the particles move up and down. This is an example of a transverse wave, a wave that displaces particles of the medium it travels in perpendicular 90 degrees to the direction of the wave propagation. So you can see that the particles move up and down, but the wave energy moves left to right. Longitudinal mechanical waves. But what happens if you move your hand from left to right instead of up and down? Observe in this animation how the wave compares to the transverse wave we just saw. What can you conclude? This animation moves a little differently. You might have noticed that the answer is that the direction of energy transport is now parallel to the particle motion. The particles and the energy are both moving in the same left to right direction. Longitudinal mechanical waves. A longitudinal wave is a wave that displaces particles of the medium it travels in parallel to the direction of wave propagation. That sounds complex, but all it means is that the medium is getting shaken left to right, and the energy also is traveling left to right. That means they're traveling in a parallel direction. Longitudinal waves travel in the same direction as the disturbance of particles. If you would anytime get confused with how these waves behave, go back and look at the earlier animations. They will show you how the wave travels differently, and that will give you a better way to imagine it in your mind. Sound waves. Sound waves are longitudinal when traveling through air and water. This means the sounds that we hear from the speakers and the sounds emitted by whales are longitudinal, as is the sound of my voice right now in this video. Remember that sound is the energy something releases when it vibrates. This energy travels through the air. For example, as the speaker vibrates, it transfers this energy to nearby air molecules. This causes the air molecules to move forward, pushing them closer together and then backwards to their original or resting position. This vibrational sound energy continues to travel forward, disturbing new molecules of the medium. However, each particle will not be transported with the energy. It will go back to its original position where it started. Particles are disturbed, not transported. When the air particles are disturbed, it's in the same direction as, or parallel to, the energy transferred. Longitudinal wave properties. We describe longitudinal waves as having compressions and rarefactions. A compression occurs when the wave compresses particles of the medium it travels in. It pushes them closer together. In our example, this is where the slinky bunches up together. On the other hand, a rarefaction is the area where the medium spreads out and the particles separate. This is where the slinky separates and the coils are further apart. These same compressions and rarefactions of particles occur when the sound waves travel through a medium, such as air. You can see a picture of this in the picture below. You can see the hand going back and forth, causing the rarefactions, or the spreading out areas, and the compressions, where the slinky is bunched together. The back and forth motion of the coils of the spring is in the same direction that the wave travels, from left to right. This makes it a longitudinal wave. Note: although longitudinal waves displace particles by compression, we can still represent them with a curvy line. You can see that here in this animation. The top shows what the longitudinal wave would look like, with the particles being bunched together in groups. And you can see how the particles are just vibrating back and forth in place. Look at the arrow, it's red, it points down at one. We can then see how the rarefactions and compressions also travel from left to right. Follow along on the bottom, because you can see in this case the peaks and crests indicate how much the particles are compressed. So we go up when the particles are really close together, and then we can draw it as down when the particles are farther apart. This indicates how much the particles are compressed. The crests are higher in the cases where the particles are compressed more. So this allows us to take a longitudinal wave and draw it as an easier to represent transverse wave and a curvy line. Wave anatomy. Despite differences in parallel and particle displacement, all waves share several common properties. We'll explore these characteristics so we can better learn to describe waves. Let's start by learning about some of the basic wave anatomy using the labeled diagram that's to our left. The dotted line cutting across the wave shows the resting position of the wave, also known as the wave normal. It is the center position about which the wave goes back and forth. For a transverse wave on a rope, this is the height the rope would be when it is at rest. For a longitudinal wave, this is where the particles would be when they're neither compressed nor rarefied, so just kind of in between, not spread out, not bunched together. In both cases, the rest position refers to the location of the particles before the wave arrives, and then the location of the particles after the wave is gone. The peaks of the wave at the very top are usually referred to as crests. More formally, a wave's crests are the highest points, the points of maximum upward displacement. On the other hand, the troughs of a wave are the lowest points, the points of maximum downward displacement. So the crest is the tallest spot on the wave, and the trough is the lowest spots on the wave. You can see that in the picture. The maximum displacement from the wave's rest position is what we know as the amplitude. This also means how far the wave travels up and away from that center rest area. When a wave periodically oscillates or goes back and forth, the amplitude is how much the displacement is from the resting position to a crest or trough. So we can measure from that green dotted line that rest position up to the crest, or from the green dotted line down to the trough. Both of these measurements would give us the amplitude, or how tall the wave is. That's how I think of it when I think of amplitude. It's the wave's height. In both transverse and longitudinal waves, the wave amplitude is based on particle displacement from where the resting position is. In a transverse wave, the amplitude is based on the up and down motion from the resting position. You can see that with the curvy lines. The black line is the rest position, and the curvy blue line or the curvy red line show you two different amplitudes of waves. Beneath those, we can see a longitudinal wave. In a longitudinal wave, the amplitude is based on the distance between the particles where the wave is compressing or the particles are bunching together. So we measure from one bunched up area over the gap and to the next bunched up area. The more compressed or rarefied the particles are as compared to their rest position, the greater the amplitude. And the best way to see this with those big words, if that's kind of confusing your brain, is just to compare the two pictures. The one on the left shows low amplitude. Look at the dots below in the longitudinal wave and look at how they are different to the higher amplitude longitudinal wave. There's a definite difference in how the particles are arranging themselves. Based on what you know about energy and your own intuition from everyday observations, how would you expect the energy of a mechanical wave to influence its amplitude? Hint: which has more energy, a tsunami wave or a tiny ripple in a pond? Answer: high energy mechanical waves have a greater amplitude. So generally speaking, when we have more energy, we will have a higher amplitude, just like having a tsunami, which is a very powerful wave with lots of energy, versus a ripple in a pond. In mechanical waves, when energy increases, so does the amplitude. And this should make sense, as higher energy will cause a greater disturbance or movement of the particles. Consider a wave in the water. When you think of a high energy wave, what does it look like? Is your high energy wave big or small? A tsunami carries much more energy than a pond ripple. The amplitude of a tsunami is much greater than that of a pond ripple. In the images below, the large wave carries much more energy than any of the pond ripples made by the bear. It's helpful to use our real-life experiences and our intuition to better understand the physics of the world around us. It helps us imagine things and really get them in our brain and understand them. The wavelength. The wavelength is one wave cycle, so it's the distance of one complete oscillation or one complete up and down pattern. This can be thought of as the distance between two neighboring crests, or 2 points. You always want to change the same point, or choose the same point on each of the waves. So you can see that in this picture, we chose the peak, the crest, in both of the waves as the point to measure the wavelength from. A period is the amount of time it takes something to repeat. So in the cases of waves, the period is the time it takes to complete one wavelength. So that one wavelength, if we timed it from crest to crest, it might be only a few milliseconds long, and that would be the period. Again, how long it takes for the one wave, to happen. Practice time! Which of the following correctly orders the waves by wavelength from longest to shortest? Take a look. I'll stop talking for a while, and then I'll give you the answers. Okay, are you ready for the answers? Let's check this out. To organize these waves from longest to shortest wavelength, we would start with B. It has the longest wavelength. Then we would go to C. It has the middle length wavelength. And then A, because A has the shortest wavelength. Time for a vocabulary summary. We're going to be seeing the words that you heard about in this presentation throughout this next week. It's important to know the words that are on this vocabulary summary so that you can talk about waves. Mechanical waves can be transverse, the up and down and side-to-side moving type waves, or longitudinal, the ones that work together going in the same type of direction, or they can be a combination of both. A transverse wave that displaces particles of the medium it travels in perpendicular 90 degrees to the direction of wave propagation or travel. So remember that transverse waves travel like the T shape that makes up the first letter of its name. A longitudinal wave is a wave that displaces particles of the medium in the same parallel direction of the wave because it's compressing or smushing together particles. So it could be shaped like that L that's the first letter in its name. Amplitude is the maximum distance from the wave's resting position. Wave period is the time it takes to complete one wavelength or one wave cycle. And a wavelength is the length of a wave cycle, so from crest to crest or from trough to trough. One complete oscillation back and forth. That's it for waves. Again, feel free to go back and look at the individual animations of anything that was in this presentation. They will help you to better understand and imagine these waves as we study them. And if you have any questions, remember you can also go back to previous lessons on any of these topics.